All right, so we did 3. I just started my recording. We did 3. We were just adding, subtracting, and multiplying. The domain ended up being the same for all of them. Let's look at 7. So we got x squared for f of x. And g of x is 1 minus x squared, the square root of 1 minus x squared. And what do they want us to do in this? We're going to find f over g and g over f and give the domain of each. So in this one, we are just dividing. So we'll do f over g of x first. So that's going to be x squared over 1 minus x squared, square root of 1 minus x squared. Is it cubed for number 7? F of x is x squared, g of x is the square root of 1 minus x squared for number 7. 8 has cubes. Oh, thank you. Yes, I missed the square up here. Thank you. Thank you. Thank you. Copy error. Is that okay now? We good? Okay. There's no simplifying to do there, so that would be the first part of our answer. Then we just need to come up with a domain of this. I see a fraction and I see a radical, so we need to deal with both of those. So I'm going to deal with the denominator first. The square root of 1 minus x squared cannot be equal to 0. Also, we have the inside of that radical 1 minus x squared. That's inside the radical, so it must be greater than or equal to 0. So we'll solve these two things and then graph, find where they overlap, and that'll be our overall domain. Hi. Thank you. 30. I'll deal with that in a second. All right, so this, I'm going to square both sides. That would get me 1 minus x squared not equal to 0. Plus x squared on both sides gets me to there. Take a square root on both sides. So x is not equal to positive or negative 1. And then for this one, we cannot solve this algebraically unless you know how to do sign charts. So this is where we may need to do a little graph. So I'm going to make a sketch of the graph of 1 minus x squared. If you don't know what that looks like, what are you going to do? If you don't know what y equals 1 minus x squared, if you don't know what that looks like, how are you going to figure out what it looks like? You put it in your calculator and graph it. So let me graph this thing, 1 minus x squared. That's the same as, I'm graphing y equals, I'm going to graph it as negative x squared plus 1. I'm hopeful that you know that that's going to be a parabola opening downwards. Y-intercept at positive 1. X-intercepts at plus or minus 1. Yes. And so it would look something like that. And I'm only interested in the portion of that graph that is greater than or equal to 0. So I'm interested in this portion up here. And that would include positive 1 and negative 1. So we're reviewing 1.2, and I'm going through it pretty quickly here. So stop me and ask me a question if you need to. My assumption is that you guys are professionals at 1.2 now. Finding domain algebraically or graphically in this case. So let's draw our number line. I have 2 things to graph, and we'll find the overlap for the 2. So this one is everything except positive or negative 1. And this one is everything between positive and negative 1, including positive and negative 1. Where do those 2 graphs intersect? Where do they overlap? Negative 1 to 1 at negative 1 and at positive 1? No. They don't overlap because I got a solid dot and an open dot. So my overall domain for this is going to be just -1 to 1. So the 1.4 portion of this question was to just stack those two things and make a fraction out of them. That's easy. But they also are forcing you to review 1.2 while you're doing this. Any questions on that? We got to finish it up because they also asked us to do G over F. Question on this one? Was that a yes? Did you have a question, Jacob? I thought I saw your hand up. No? Okay. G over F of X. So we just stack it the other way. This time we'll put the square root on top and the X squared on the bottom. So that's easy. That's the new stuff. Now I just got to go back and practice what we learned in 1.2, which is looking at that function and finding the domain of that function algebraically. So what restrictions do we have this time? We have a fraction. The denominator of the fraction must be not equal to 0. So we'll solve that. We'll get x, take a square root on both sides. We get x not equal to 0. We also have a square root inside of our function. So the inside of our square root restriction is it's got to be greater than or equal to 0. And then we want to solve that, which we already did. We did that over here. So I'm just going to borrow that solution. So let me graph these two on top of each other and we'll see where they intersect. So this one would have an open dot at 0, but it would be a graph everywhere else. And this one right here, we just graphed over here. It's got closed dots at -1, +1, and it's graphed in between. So where do they overlap? I'd say they overlap at -1, agreed? And then everywhere between -1 and 0, but not at 0. They overlap over here to the right of 0, but not at 0, and then everywhere up to +1, including at +1. So that would be our overall domain for that function. Any questions on 7? Pretty involved there. Just the domain part was the trickiest part there. Yes? So if we have a radical anywhere in the function, it doesn't matter where it is in the function, we have to take the inside of that radical and put the restriction of any radical, which is greater than or equal to 0. Square roots in it. If it's in the denominator, then yes, you got to take care of it. You got to take care of both things. Okay, so the entire radical is in the denominator, so it must be not equal to 0. Of the entire denominator. Doesn't matter whether there's a radical, there could be 10 different radicals in it, all kinds of stuff. But whatever the entire denominator is, that needs to be not equal to 0. Okay, the bottom of the fraction, the entire bottom of the fraction. So you got to think about the fraction as a whole. It doesn't matter that there's a radical inside of it. The whole bottom of the fraction is not equal to 0. Okay, and then separate from that, yes, I do have a radical. It doesn't matter that it's in the denominator, could have been in the numerator. We still would have needed to apply this to it. So don't start trying to come up with special rules for when there's a radical in the denominator. There are some if you want, but you're just making things more complicated than they need to be. Okay, anything that's in the denominator, take the entire denominator, no matter what it contains, set it not equal to 0 and solve it. And then go back and look and see, do I have radicals anywhere? Don't worry about whether it was already part of your denominator. If you had a radical someplace, you still need to deal with the inside of it. That's my recommendation. You can get really complicated and say, well, if there's a factor of the denominator that is a radical, rather than taking care of it twice, you can just say greater than 0 because it can't be equal to 0 because it's a factor of the denominator. That gets confusing though. You're better off just treating them as two separate rules, okay? And if you end up having to deal with something twice because it's both in the denominator and inside of a radical, that's okay. Just deal with it twice. Okay. Question? Did you have a follow-up? Mm-hmm. Yep. So think of when you approach these, if you're having trouble separating them, just think of this as a box. Whatever's in the bottom of this, that box, that's all of that gets packed inside of a box, and that entire box cannot be equal to 0. Okay. Because it's in the bottom of a fraction, because we can't divide by 0. And then separately come back and look inside the box and see if there is a radical in there. If there is, take that radical and set it greater than or equal to 0. Because it's got to be. Because the inside of a radical has got to be greater than or equal to 0. And again, remember, we're dealing with numbers here, right? So the bottom of the fraction, whatever it is, that whole number, whatever it is, cannot be 0. We can't divide by 0. Yep, we're dealing with them separately. Yep. There is a way to combine it together. I've tried teaching it that way. It gets really messy and confusing. I'd say just your best bet is just to think about the rules. Right now, there are 2 rules. If you see a fraction, the entire denominator is not equal to 0. If you see a square root, the entire inside of that square root is greater than or equal to 0. We'll add restrictions for logs and inverse trig functions later on as we go. So we'll add, but right now, those are the only 2 things that we're looking for. All right, any questions on 7 before we move on to our next section, which is 11 to 20? 11 to 14, I'd be happy to do any of these, 11 to 14. Does anybody have a preference? We're doing them all. It didn't say 11 to 20 odd. Probably an even one would be a good one for us to do together right now, because the odd ones have the answers in the back of the book. So 12 or 14, who's got a preference? 12 or 14? 14 it is. So in 14, they defined f of x as x over x plus 1 and g of x as 9 minus x squared. And they want us to do what? They want us to find f of g of 3 and g of f of negative 2. I'm going to write this a little differently than they did. They wrote it with the little empty O thing. I prefer this notation. We're going to do that, and then we're going to find g of f of negative 2. So let's start by finding g of 3. What is g of 3? G of 3 is 9 minus x squared, but we're putting a 3 in place of that x. So it'd be 9 minus 3 squared, which is 0. So g of 3 is 0. So I'm going to replace the g of 3 with 0. We just figured out that g of 3 was equal to 0, so we'll just replace it. Cool. And then we got to do f of 0. So my f function is x over x plus 1. We'll put zeros in both of those x's. We got 0 over 1, so we end up with a final answer of 0. So f of g of 3 is 0. Do we have questions? Can you guys pause the side conversation until we get done going over a few? Sorry. You put undefined? For this one, it's not undefined. We can do it. We were able to find both the g of 3 and the f of 0. All right, let's do the second one here. We got f of negative 2 is on the inside, so we'll try and do f of negative 2. So f of negative 2 is going to be x over x plus 1, but we're putting -2 in both of those spots. We get -2 over -1, which is +2. Mm-hmm. This is totally a new thing here. So this doesn't rely on what we did over here at all. So they asked us to do two things. They asked us to do f of g of 3 and g of f of -2. So we finished f of g of 3, it was 0. I'm working on g of f of -2. So I plug -2 in to my f function, I got 2. And then we're going to take g of that to get our final answers, which would be 9 minus 2 squared. So 9 minus 4 is 5. Our final answer. So g of f of -2 would be 5. We got on 14. All right, and then what do we do next? We went up to 20. So 15 to 20. This is kind of where we ended up in our notes on Thursday. We're finding g of f of x and f of g of x, and we're finding domain for each of them. So does anybody have a preference? 18 would be a good one. 18 and 20, you got it. We'll look at 18 and then we'll at least start 20. But we'll do 18 start to finish here. So let me write down my function definitions. F of x is 1 over x minus 1. G of x is the square root of x. And we're going to find f of g of x and g of f of x in the domain for each. So since we're dealing with domains, I think it's probably smart for us to find the domain of the individual functions. We talked about how we have to deal with that for these. So before I even get started, I'm just going to go ahead and find the domains for each of these individual functions. Okay, so the domain of this one, let's see here. I got x minus 1 in the denominator, must be not equal to 0, so x is not equal to 1. So my domain here is anything except for 1. So we'll keep that in the back of our head. And for g, my domain, what do we see? I see an x, it's inside of a radical, so it must be greater than or equal to 0. So my domain here is going to be 0 up to infinity. We'll keep that in mind also. All right, so now let's go ahead and begin doing the part that they asked us to do. So they want us to do f of g of x. And we're just going to do some messy substitution. We'll find the domain of our overall final product, but we'll keep in mind that we may need to also include the domain of g of x into that. And the domain of g of x is only 0 to infinity. So I'm just going to make a note that that could potentially end up getting added to the domain of the overall product. You guys remember why we have to do that? Because anything that's going to go into f of g of x is going to go into g of x first. So we got to make sure it's not going to break g of x. And these are all the things that'll work inside of g of x. All right, now let's go ahead and write out what f of g of x is. So I'll start by substituting whatever I can. I can substitute something in place of g of x. G of x is equal to the square root of x. And then I'll go ahead and take that square root of x and plug it back into my f function. That was 1 over x minus 1, but it's no longer an x. We'll replace it with square root of x. clean that up. It doesn't really need the parentheses. It's 1 over the square root of x and then minus 1. And that's f of g of x. We just need to find its domain. This will be a good time to practice what we were just talking about a second ago, right? So let's find the domain of this thing. I see two potential problem areas that I'm going to have to deal with. I see both a denominator and a radical. So we're going to deal with them separately and then combine them together. So let's do the denominator first. The denominator is the square root of x minus 1, and that must be not equal to 0 because it's a denominator. So I took that entire denominator, set it not equal to 0 because that's what we do with denominators. And we solve that, add 1 to both sides, we get that, square both sides, we get x is not equal to 1. But that's not all we got going on here. We also have this radical. Disregarding the fact that it's in a denominator at this point, it's just it's just a radical. We've already dealt with the denominator. The inside of that radical is x. And what do we know about x? If it's inside of a radical, it must be greater than or equal to 0. And at this point, I'm noticing that's identical to what we already had over here. So this isn't going to really come into play because we've already got that restriction here. This isn't adding any new information because it's already part of what we would do here. So to find my overall domain, I'm just going to graph those two things and see where they overlap. So x not equal to 1 and x greater than or equal to 0. If I hadn't been looking, I might have added this onto it also, but it would look exactly like this. Okay. In fact, why not? Doesn't hurt. We'll put that 0 to infinity on there from the original restriction, and we'll find every place that works for all three of those. And technically it's just 2 because these two are identical, right? So it looks like the domain does include 0. We're overlapping at 0 all the way up to 1, but not including 1. We pick up the other side of 1 and go up to infinity. So that would be our overall domain for f of g of x. Mm-hmm. We found this because in order to do f of g of x, remember when we put those machines together in that factory, x is the input for the overall factory, but it's got to go through the g machine first. So we got to make sure that it's not going to break the g machine. So this just is what's going to keep x from breaking the g machine. These two things are what's going to keep it from breaking the factory overall. It turns out that since these are identical, this didn't really come into play. But we will sometimes see where we get some stuff over here, and then there's extra stuff over here that we also have to cut out. And we saw that in that example that we looked at together on Thursday. So a lot of times, this doesn't actually end up making a difference. It ends up being included already in our final function, but sometimes something happens in the final function where like a square cancels a square root, and you have to also add this in. It ends up being different from what you get over here, and that needs to become part of our domain. We didn't really have to include the purple because it's identical to the green that kind of came out of this original. All right. We'll do g of f of x now. Same thing. I'll keep in mind that the g function or the f of x function has a domain where x cannot be equal to 1. So we may need to add that in at the end. I'm guessing probably not, but we may need to. So we'll keep it in mind. So let's do some substitution. We'll keep g and replace f of x. F of x from the original problem was 1 over x minus 1. That's pretty messy. And then we will do our g function on 1 over x minus 1. Our g function is the square root of x. we're plugging 1 over x minus 1 in place of that. And that doesn't really simplify either. Well, we could do the square root of the top and the square root of the bottom. The square root of 1 is just 1, and then we could do square root of x minus 1 down here. Bless you. So I'd say that'd be our simplified version. Let's practice finding our domain. So we have two things going on. Do you see both of the things? You see we got something in the denominator and something in a radical. So the denominator, we'll focus on that first, was the square root of x minus 1. That must be not equal to 0. Bless you. And the radical was x minus 1. In the inside, that must be greater than or equal to 0. We solve those two things, we're going to get, let's see, square both sides. Add 1 to both sides. So x can't be 1. Oh, look, that ended up being identical to this over here. So this didn't really add any new information, and it already kind of came out that way here. And then here we'll get x greater than or equal to positive 1. You could sketch those two things, but I'm pretty confident saying that that's just x is bigger than 1, but not equal to 1. Right, so my overall domain would be 1 to infinity, but not including 1. And if that doesn't pop out at you, just go ahead and sketch these two things, find the overlap. So there's 18. There's a question about 20. Let me do 20 as kind of individual questions. I'll tell you this, though. In 20, you're dealing with cube roots. There are no restrictions on cube roots. I can't remember who asked me about 20. There are no restrictions on cube roots. So in number 18, I'm sorry, in 20 rather, you've got this cube root of 1 minus x cubed. This g of x has a function, or the domain all real numbers. Anything's going to work fine in there. So I'll address questions on that individually. Let's keep moving here. I want to go over a couple more with you. What's the next section? 23 to 25. Okay, these ones are ones that my students in the past have had trouble with, but like once you see one of these, you're going to find it really simple. So 23 to 25. I feel bad because I'm gonna you're not gonna have much to do for these once I show you one of them. That's all right. Here we go. Does anybody have a preference? 23 to 25? How about 20? Let's start with 23. So they gave you y equals the square root of x squared minus 5x. And they want you, the instructions are telling us to transform that into an f of g of x. So it's still x squared minus 5x. And all they want you to do is come up with an f of x and a g of x that when you put them together, you could get this as your answer. Once you've seen one of these, you're like, oh, that's all they need us to do? That's not that big of a deal. So if you looked at this square root of x squared plus 5x, what kind of looks like it's sort of on the inside of the whole thing? X squared minus 5x kind of looks like it's inside, right? And we want the g of x to be the thing that's inside. I'd say the inside is x squared minus 5x. What would I put x squared minus 5x into in order to get this function? Square root of x. And that's it. That's number 23. That's it. Is that way easier than you, if those of you who looked at this, is that way easier than what you thought it was going to be? Right? Should we do 24 while we're here? So I'm just going to write it out as f of g of x. And they told us in the book, they wrote it as y equals, I'm writing as f of g of x. It's y cubed plus 1 squared. So I need to come up with an f of x and a g of x so that when I put g of x into f of x, I will get this. So what kind of looks like it's on the inside of this function. X cubed plus 1 is kind of on the inside of it, right? On the inside of what? X squared. And that's it. Question, yes? Yeah, any questions on 23 or 24 before we go back to the previous one? Are we good on these two? Yep. Yeah, so the question is, what happens if this restriction here that we did for just the g function, what if it doesn't match one of these restrictions that we came out with over here? If that happens, then we go ahead and graph all of them. This one and this one and this one. We graph them all and we look for where all of them overlap. And I kind of showed that on this one. I graphed all three of them. No, a lot of times it's going to end up matching one of these things, but every now and then it won't, and you'll have to consider it as well. Right? So the example that we looked at on Friday, let me just show you an example here real quick. So this one, here's my two functions, and don't worry about trying to write this down because this is on Canvas. Just look though. Here's my two functions. Notice my g of x has a square root inside of it. So I would say x plus 2 greater than or equal to 0, and I'd solve and I get x greater than or equal to -2. So this is my domain for the g function, and I'm going to keep this in mind. When I go through and plug everything in, I end up getting the final function of x squared plus 4, which has a domain of all real numbers. I got to put those two things together, and if I were to actually graph them, here's my -2. One of them would be all real numbers, and the other one would just be from -2 up to infinity. So when I went to find the overlap of those two things, it would be from -2 to infinity. So this is an example of one where this restriction did not end up coming out at the end, so we had to include it and graph it along with what came up with at the end, find the overlap of those two things. Are we feeling better about that? Yeah, it's a minor detail. I'll tell you, there's going to be one on the test where you'll have to add it in, right? And if you forget to do it, you might lose a couple of points. It's not going to be like enough to make the difference between an A and an A minus on the test, though. So. All right, what's next? Let's do 31, since it's the only one in its section. High altitude spherical weather balloon. All right, so this is an example of where we use these function compositions in the real world. This happens a lot, that a function goes into another function. All right, high altitude spherical weather balloon expands as it rises due to the drop in atmospheric pressure. You guys understand that? When it goes up, the pressure gets less, so the balloon expands. So if you've ever seen them put up one of those balloons before, when they're launching them off the ground, they look like they're barely inflated, right? And that's on purpose, because if they were full on the ground, when they went up in the upper atmosphere, they would pop, because they're gonna expand even more. All right, so suppose the radius r increases at the rate of 0.03 inches per second, and that r equals 48 inches at time t0. So I'm going to make myself a little t chart here. This is time. This is radius. Let's make sure I understand this. This looks like a linear function. At time 0, the radius is 48 inches. And then every second, where the radius is increasing by 0.03 inches per second. So just to make sure we understand this, after 1 second, what is the radius going to be? 48.03. After 2 seconds, the radius is going to be 48.06. You get the idea? Do you think you could write me an equation for r as a function of t? So going back to algebra 1, it would it's linear, right? It's going to be like y equals mx plus b, except we're using t and r instead of x and y. So the thing in front of the x, this would be like the m, and y equals mx plus b. What is that? Is that going to be the 48, the initial value, or is that going to be the 0.03, the change? It's the slope, right? M is the slope and y equals mx plus b. We're writing a linear function here, folks. This is one of those things that we will not be reviewing in pre-calc. So if you don't know how to write equations in y equals mx plus b form, go do a little internet research. The rate, the slope would be 0.03 because that's what I'm changing by each time. And the initial value would be 48. This would be my equation for R and T. Okay, that's my assumption that you can do that in your sleep at this point. If that's not true, go back and review it. We okay on R? All right, what else did they tell us? Determine an equation that models the volume of the balloon at time t and find the volume when t equals 300 seconds. So now we need a volume formula. Volume is related. Now this is a spherical. It says it's spherical, so we need the volume of a sphere. What parameter goes into that? What do you need to know about a sphere in order to tell me its volume? You need its radius. Hey, conveniently, we've got a formula for radius. Let's write the formula for the volume of a sphere. Does anybody know it? If you don't know it, where could you find it? Internet. It's also right in the front of your book, I think. The front or the back. Yeah, here it is, right in the front. The volume of a sphere is 4/3 pi r cubed. So this is a great example of, I don't know what the volume of a sphere is. That's all right. I didn't know that off the top of my head either. But I was able to find it. So they want us to write an equation that models V as a function of T. Now I've got an equation that models right now. I've got an equation that models R as a function of T, and I got an equation that models V as a function of R. So how am I going to get V as a function of T? Yeah, we're going to do a little substitution. We'll pull this R out. What are we going to put in place of there? 0.03 T plus 48. So we're taking this function and plugging it into this function. That's the very definition of a composite function. We've been practicing that, but we've been doing it kind of more abstract way. So the volume function was 4/3 pi r cubed. We'll just take our r function and plug it into there, 0.03 t plus 48. So there we go. That's good. And then we would just leave it like that. We're not going to mess around and try and expand that or something. That would get super messy. So there's that. And then I'll leave the last part to you. They want you to find the volume when t is 300 seconds. How are you going to do that? You put 300 in for t, that equation. Beginning of chapter 2, we will be really quickly reviewing linear functions, but I'm hopeful that if you're given a rate and a starting value that you can write an equation like this. And if you're not sure how to do that, spend some time on the internet or schedule some time with me. We can go over it. That would be like a 10-minute sit down, and we could have you doing just fine with that again. 45 to 49. You know what? I'm going to let you guys mess around with 45 to 49. We'll go over questions from that on Wednesday. So I've talked enough at you. That should be enough to get you a good start on that assignment. So you have the rest of the period today